to Taylor series and Taylor polynomials. This is for Calc 1. We will just limit ourselves to the to the linear approximation. Well, a linear approximation is ultimately just finding the equation of the line that is tangent at a given point on the given graph of the function. You know, that's basically, okay, the slope right here is the derivative evaluated at that value of a times x minus a. Well, that's the remaining factor, and the last term f of a is the y1 value. All right. These linear approximations, furthermore, we can use them to estimate weird values. You know, like finding, I don't know, the square root of 28, for example, right? No, not the square root of 28. Let me do the square root of 17, for example. Well, clearly that number, square root of 17, it's not a perfect square. However, this 17, it's pretty close to another number that is a perfect square. What number is this? So, from the square root of 16, which is 4. Well, we can also evaluate the cube root of, I don't know, maybe 29, all right? However, the number 29, it's not a perfect cube in this case, so we can evaluate the cube root. However, there is a number pretty close to 29 that is a perfect cube. Can you tell what number is that? 27. So yes, 27. All right. Even, I don't know, maybe sine of 31 degrees, or let's see, 32 degrees, right? Well, unfortunately, well, the 32 degrees, it's not a number, it's not a special angle like the ones that we know from the unit circle, like 30 degrees, 45 degrees, or 60 degrees, or its multiples if we go around the whole unit circle. So, however, this sine of 32 can be approximated via, okay, what would be the closer angle that we know its special value or its exact value? 30 degrees, right? And a bunch more situations we can approximate these values, all right? Okay, so let's go about the first example. And this is usually the nicest presentation of this type of problem, because number one, they're asking us to find a linearization of the function f of x equals the square root of x at 49. They're telling us which function at which value, and then they're asking us to use the estimation, or the linear approximation for this function to estimate the value of the square root of 50. Okay, so number one, let's find the linear approximation of this. So we are essentially looking for the equation of the tangent line. So to find the equation of a line, there are two pieces of information. What are those two pieces of information again? For the equation of a line. The slope and what else? The y-intercept at any point in general, right? Well, so to get the slope, we need to find the derivative of this function, and then we also need to find the related order pair. So that's f of 49. That's the square root of 49, which is 7. So in this case, we are around the order pair 49, 7. All right. So we already have the point. Now let's go about the slope. So to find the slope, we need to find the derivative. So f of x, which is square root of x, which is x to the 1/2. So we cannot differentiate this radical just the way it is. We need to change this to the rational exponent notation. And here's the general power rule. Take f prime. So that's 1/2 x to the negative 1/2, which is 1 over 2 x to the 1/2, which is 1 over 2 root of x. All right. So this derivative is an expression to find the slope of the function square root of x at any particular value of x. Well, in this case, we're interested in the slope at a equals 49. So let's evaluate. So the slope m will be the derivative evaluated at 49, which in this case is 1 over 2 times the square root of 49, which is 1 over 2 times 7, which is 1 over 14. So that's the slope. I'm going to write m again. So to have a sense of continuity here, well, from this order pair, okay, let me write this order pair below. The order pair is 49 and 7. This, the first component of the order pair, will be our a, and this is our f of a. So from the linear approximation, so this means, okay, that f of x is approximately f of a plus f prime of a times x minus a. So that's our generic form, or generic formula, if you will. Let's put it together with what we have in our problem. So number one, I would like to replace f of x with the square root of x. So in this case, this is what we're saying, that the square root of x, the function square root of x, is approximately f of a, which is 7 plus f prime of a, that's 1 over 14 x minus a, which is 49. So that's our linear approximation, right? So that's our linear approximation. Well, now we're going to use this linear approximation to compute or to estimate the value of the square root of 50, all right? So, and in this case, we're not going to use any decimals. We are going to leave it in exact form. Well, so here is the thing, guys. This is the best advice I can give you about linear approximation. I know this looks very tempting to be distributed, but leave it like that. Do not distribute. I will show you why. Leaving it like this without distributing, it's going to simplify our calculations a lot when we compute the value, in this case square root of 50, that is approximately 7 plus 1 over 14, 50 minus 49. In this case, well, let me highlight what we are substituting. X equals to 50. Alright, and square root of 50, it's approximately 7 plus 1 over 14 times, what's 50 minus 49? 1. Isn't that just 1? And well, so 7 plus 1 over 14, have a 1, how about multiply by 14, divide by 14 to get the common denominator, so 14 times 7. 98. Okay, so 98 plus 1, that's 99 over 14. Alright, so the square root of 50 is approximately 99 over 14. Alright, how about we check that with the graphing calculator? So let me open the graphing calculator real quick. Okay, so what was that? 99 over 14. So that's 7.07. And what's the square root of 50? I think it's a pretty close approximation, isn't it? It's a pretty good approximation. Let's do another example. And the next example, it's pretty much the worst case scenario. They just tell you estimate the value of the cube root of 26. And that's it. They're not telling you anything else. Well, so in this case, there's a lot of stuff that we need to figure out on our own. Number one, to guess the function. And number two, to look for a value of a that is close to 26, that it's a perfect cube in this case. All right, so, okay. Let's do one at a time. What would be a good function to relate to this? The cube root of x, right? Because we have a cube root of some number, so that's the cube root of x. And at which value of a equals to, well, we need to find a number closer to 26 that is a perfect cube. What would be that number? 27. Correct. Okay, let's go about the differentiation to find the slope. Oh, so f of a, that's the cube root of 27, which is 3. So we're going to have the order pair 27, comma 3. All right. Now, okay, let's do the, oh, it's not 1/2, it's a 1/3 actually. So y prime equals to 1/3 x to the, okay, 1/3 minus 1, isn't that negative 2/3? And that's the same as 1/3 x to the 2/3. Well, how about we change this into radical notation? And I'm going to do the following. I'm going to write this as y prime equals to 1/3. So the denominator of the rational exponent here, this denominator is going to tell us the index of the radical when we change the notation to radical form. So that's going to be indeed the cube root of x, and I'm going to square this number. I'm going to leave it like this, not the other version where we have this square power inside, because it turns out that for x equals 27, we can again find the exact cube root and then square it. Otherwise, we would have to play with powers of the number that it's not a perfect cube. So now let's find the slope. M, which is the derivative evaluated at 27, that's 1/3 times the cube root of 27 quantity cubed. Okay, number one, what's the cube root of 27 again?
It's squared, not cubed.
Yes, that's what I meant. Thank you. So it's 3. And then this 3 quantity squared, isn't that 9? And that 9 times 3 in the denominator is 1/27. Alright. So that's 1/27. So we already have the slope. We have the point. We may go about the linearization of the function. So this means that the cube root of x is approximately f of a. Well, let me write down the generic formula again. F of x is approximately f of a plus f prime of a x minus a. So we're going to adapt this to our problem. So that's f of a, which is 3, plus the slope, which is the derivative, 1/27 times x minus 27. And again, don't attempt to distribute this to make our calculations easier, alright? So we may use this linearization to compute the cube root of 26, and in this case 26, well, oh, that's a plus, so so that's going to be 26 minus 27, isn't that a negative 1? So that's 3 plus 1/27 times a negative 1, or 3 minus 1/27. Well, let's combine these numbers together to get an exact answer. So that's 27, and 27 times 3, well, that 27 times 4 is, I believe, 54, and 27 times 3, I believe, is 81. So 81 minus 1, that's actually 80/27. All right, so that's our approximation of the cube root of 26. Again, how about we verify this using the calculator to find out how big how good this approximation is. Well, so 80/27, so that's 2.96. Now for the cube root, I would like to go, okay, so the cube root of 26, so that's a 26 basically raised to the 1 over 3. That's the same as saying cube root. And I think this is a pretty good approximation again. I mean, this is an okay, it's not a bad approximation, it's a good approximation. However, like I mentioned before, when you get to calculus 2, you're going to expand this linear approximation and add more terms, a quadratic term, a cubic term, a quartic term, quintic, many more terms to make this approximation even better and closer to the actual value. Now, so one of the things that we want to look when it comes to doing these approximations is to have an idea of whether these approximations are overestimates or underestimates. For example, well, how are we going to know that? Well, let's look at the graphic approach. So for the graphic approach, well, so suppose so it's kind of big. So suppose we have this function f of x, and we choose to find the equation of the tangent line at a given point A, whatever that point is. So let's trace its tangent line. So in this case, notice how the derivative, which is the slope, it's a positive value, right? So in this case, we will conclude that we will have an overestimate if it's an overestimate if the slope, the derivative, is greater than 0, is positive. Because notice how when we try to evaluate, for example, for the square root example, is suppose we have the square root, what did we do for the first one? Did we do, okay, we did 49. So suppose this is the number 49 and this is 7. So that estimate that we obtain, or rather that approximation that we obtained using the linear approximation, in this case it was for the square root of 46, I think it was, or 50, right? So notice how this value is slightly bigger than the actual value. And if we go back to the graphing calculator, square root of 50, 7.07106, that's the actual value. But the approximated value, do you see how it is slightly bigger? Because it is slightly bigger, then, well, in this case, we have an overestimate. I mean, it's not like the largest overestimate, but I mean, just by slightly decimals. And we will have an underestimate if we have, for example, a decreasing function, you know. And in this case, we trace our tangent line, and notice in this case how the approximations on the linear approximation are values that are below the actual values. And we know that also by looking at the value of the slope. So in this case, if the slope is negative, it's an underestimate. So if, I mean, underestimate if the derivative is less than 0, it's a negative value, right? And again, well, I don't have an example with an underestimate, but at least, okay, let's verify whether, for number 3, determine whether the approximation in example 1 is an overestimate or an underestimate. Well, we already did it by comparing the numbers, right? However, we are going to determine by the value of the slope. In this case, what did we get for the slope for example number 1? I believe we got, so what was that? 1 over 14, right? So m equals 1 over 14. Now, is this value of the slope positive or negative? Positive, right? Since it's positive, then it's going to be an overestimate, right?
So anything positive is overestimate, anything negative underestimate.
Exactly, and that's going to depend on the nature of the function that we have, because, well, for this curve in the overestimate, we have the slope lying above the function, so that's going to give us, the approximations are going to give us values that are slightly larger than the actual values. And on the other hand, for a decreasing function, the slope or the tangent line is always going to lie below the graph of the actual function. So when we use this linear approximation to estimate values, for example, what if this is 3 and this is, I don't know, maybe 3.2, all right? So if I use the linear approximation to estimate the 3.2, do you see how it's slightly below the actual value? So that's for this reason, well, graphically, that's going to tell us it's actually an underestimate. And well, we can always tell by the sign of the slope that we obtain as we progress getting this linear approximation. All right? And well, yeah, so that's about linear approximations. The next topic is finding the differential. So a differential, it's usually a way to estimate the amount of function or how much a function changes when we make a slight change in the independent variable. Okay, so for example, think about when you wrap a gift. You know, when you wrap a gift that it's a perfect, that it's a rectangular box. That rectangular box, you get the dimensions, find the volume of that box, but you are going to add a layer of paper to wrap the gift, right? But that layer is very thin, if you will. However, that thin layer of paper, it's going to be an increment in the volume of the box. Maybe not by much, but it's going to be something. You get the picture of what I'm talking about? Okay, so we're going to use calculus to determine that change in the dependent variable when we make a change in the independent variable. But first, we are going to treat this like functions in terms of derivatives. All right. So here is the thing. This function y equals f of x. When we take the derivative, and I'm going to use Leibniz notation, dy dx, that's f prime of x. So up to this point, we have thought about this dy dx as only one symbol to determine, oh, y is varying with respect to x. So we're looking at the rate of change of y with respect to x. But this time, in differentials, we will finally look at this symbol as the quotient of two quantities, because yes, it looks like a quotient, right? So what we're going to do here is multiply both sides by dx, cancel, and this becomes dy equals f prime of x dx, which is exactly what we have above, right? All we're doing is, in a nutshell, all we're going to do is find the derivative of the function using Leibniz notation, not the prime notation, and multiply both sides by dx. That's it. Let's do one example for this function. So the derivative dy dx equals, so that's 5e to the x squared times the derivative of x squared, which is 2x. And simplifying this is 10x e to the x squared. Now, we don't want just the derivative, we want the differential, so all we have to do is multiply both sides by dx. That's it. All right?
We'll just leave tx by itself.
Exactly. We just leave, the dy equals by itself.
What does that actually tell us?
the application in the next problem is going to answer that question. So we right now we did it as a practice with a generic function of x, but now in the applied context, check this out. So what? The radius of a sphere is measured to be 21 centimeters. But sometimes, well, when we're using these rulers or these calibrators, these devices sometimes tend to be inaccurate by some tolerance, right? But so it turns out that the ruler or whatever measuring the question.
Yes. So how did 2x
By the chain rule, the derivative of x squared is 2x.
So you just use the chain rule?
Yes, so the derivative of the exponential, which is itself the exponential, times the derivative of the exponent, which is the derivative of x squared, which happens to be 2x. And then just simplify the coefficient. Right? Okay, so this sphere was measured with a ruler or some calibrator or whatever, and well, the manufacturing, statement tells us that, well, these measurements could be of an error of at most 0.05 centimeters. All right? So this is what we're going to do. We will find the volume of the sphere of a radius equal to 20 centimeters. But if we make a slight change, that is, adding those 0.5 centimeters, that volume will be slightly larger. All right. So this is what we're going to do for now. So let's think about, well, it's a sphere and it's all about volume. Let's use the formula for the volume of the sphere, which is 4/3 pi r cubed. Now we're going to take the derivative of the volume, but be careful because we just looked at related rates problems last class and during the last couple of lectures. However, in related rates, it is both variables, the volume and the radius, changing over time, right? So don't get confused with this type of problems, because in this problem, it's not about changes over time. So we're just going to take the rate of change, which is the derivative, dv dt, not dt, dr. All right? And well, that's 3 times 4/3, which is 4 pi r squared. All right? These are not changing over time anymore. And well, we're going to find the differential in a similar way that we did before. So we're going to multiply both sides by dr. Are you all right? I know, it's this weather changes, right? Yeah, I hear you. dv, okay, cancel the r's, dv equals, so that's the differential 4 pi r squared dr.
That's the final answer then.
Huh?
Is that the final answer?
The expression. So now we are going, so when we plug in, r equals to 21, and this slight change, the possible error, which is the dr, so dr is going to be 0.05, and the radius, which is given, that's 21. So this will be, so the dv, oh come on, 21 squared times the r, which is 0.05, and simplifying this is approximately 277 centimeters cubed. So this is how we will interpret the result. So this means that, not v, it's actually dv, right? So this means to interpret this result is, in words, increasing the radius by 0.05 centimeters has an effect of increasing volume by 277 centimeters cubed. So if we find the volume of the sphere for 21, well, we're going to get a number. However, if we add, I don't know, maybe a very thin layer of paint, for example, to that sphere, which could be this 0.05 centimeters, is really tiny. So that adds 277 additional centimeters cubed to this big, to this already, well, 21 centimeters. I'm gonna get like this, you know, like a soccer ball, I guess. So 21 centimeters, and that thin layer of paint will add 277 centimeters additional centimeters cubed. Well, so that's one way to visualize these changes. Another way to visualize these changes is by percentages. Question?
I was going to ask about that.
Oh, okay, yeah. The second part, right, on that it's typed. So now we're going to express these errors as percent. Well, so recall that to express this as percent, all we have to do, well, in this case, I'm going to divide dr over r, that is the change, the slight change in the radius divided by the whole radius. So all we have to do is write down dr, which is 0.05, by the total radius. Well, in this particular situation, we're looking at the radius equals to 21. And using a calculator, this should give us approximately 0.0024. All right? Well, what are we, so when we add 0.05 centimeters to an already 21 centimeter radius sphere, we are increasing the radius by 0.24%. All right? So we're making it 0.24% bigger about the radius. Now, what about the effect in the volume? So in this case,
You said 24% bigger. It's not 24% bigger, right? It's
0.24 exactly. So we're going from this decimal, good question, and we move the decimal two places to the right to express this as a percent. Yep. Now, what about the volume? So what about dV over the total volume? Well, in this case, this would imply to calculate dV, which we already have, and divide by the calculation of the total volume, but I don't want to plug in values and simplify. So here's what I'm going to do. I'm going to write the expression for dV in the numerator, which we got 4 pi r squared dr, and divide this by the volume of the sphere, which is 4/3 pi r cubed. All right, so let's do some simplifications here. So I'm going to simplify. I'm going to cancel out these 4's, and this division by a third is going to be a multiplication by 3. So that's a 3. We can also cancel, we can divide out the pi's, and we can divide out the 2 powers of r with 2 out of the 3 to remain with only 1. So that's going to leave us with the following: 3 dr over r. You guys following me here? Well, this is the same as saying simply 3 dr over r, but what's dr over r? Didn't we compute it before? This is 3 times 0.0024, and if we multiply these two numbers, we get approximately 0.007, which in percent is 0.7%. How about we write a statement here, a sentence to summarize this result? So, a 0.24% increase in the radius implies a 0.7% increase in the volume. So did you see the effect of slightly modifying the independent variable, which in this case is the radius? Just modify the radius by 0.24%. That's going to make a big increase in the actual volume, right? It doesn't seem like much, but I mean, the more you add, it actually, well, it adds up, right? So that's what this differential tells us about the effect of slightly modifying the independent variable on the dependent variable. All right, and this is all I have for today.